Hey guys, welcome to another YouTube video. It's been a long time since we've posted anything, obviously because of the lockdown, and in our country it's an indefinite lockdown until further notice, so a little bit of an unfortunate situation. However, we are here with another video for you guys to keep the technical content going, and to let you guys know that we're still here and we're still doing a lot of R&D in the background, even though we are shut officially because of the lockdown. So you'll obviously notice a different background as what you'd normally associate the background to be with the flames in the housings. Anyway, the video for today is going to basically be a long one. It's going to be a 2 or 3 part video. I'll still decide on how long that's going to be and what we're going to be including into it, but it's about hybrid turbos once again. Now, there's a lot of interaction on YouTube, and there have been a lot of emails and comments flying around, and we love the constructive criticism. We absolutely appreciate the comments, the suggestions, the queries, and all of the constructive criticism about the videos we make, the content that we have, and we encourage it. And I remember one of the emails that came through was from a guy that said, look, you guys have gone and made so many videos about hybrid turbochargers and the failures and the shortcomings and the problems, and you're a bearer of bad news. Why don't you guys show us how you build a hybrid turbocharger? How do you guys upgrade a turbo from a stock to a hybrid status? Challenge accepted. And that's what this video is about. So today what we're going to be doing is we're going to be taking a 70 and 79 series V8 Land Cruiser turbo, which is a Garrett GT22. It's a journal bearing turbo, VNT. It fits the 4.5 litre V8 diesel engine, and we're going to basically build a hybrid from there. But what we're going to do is we're going to show you step by step absolutely every single thing we do, from taking the turbocharger, which is removed from a vehicle. We're not doing a hybrid to a new turbo. We're taking a turbo that has just been removed off a vehicle, a running vehicle in good condition, low mileage, nothing wrong with the turbocharger. We're going to disassemble in step-by-step format to show you guys how we do it, what we look for in the disassembly. Once we've disassembled the components, we'll lay them out and show you what we replace inside that turbocharger. We inspect the compressor wheel, we inspect the shaft, we inspect the bearing system, etc., to make sure that we are not setting ourselves up for failure. And a lot of people don't know how to do that, and a lot of people offering hybrids don't do that. We'll also show you the replacement components, whether or not they're able to be reused or not. We replace certain critical key components inside the turbo, so we're going to go into all of that as well. We will show you the program that I wrote for the CNC lathe. Yes, CNC. We CNC profile the housings. None of our hybrids are built by machining compressor housings by hand. A lot of the local guys in our country do not have access to CNC machines, and they do this by hand. There are inherent problems associated to that. Clearances are incorrect. The radius profiles, you've lost the unilateral or the coincident profile between the blade and the housing, so you'll find that these irregularities, it does cause certain issues. There's also the case where repeatability is always going to be of concern, and you'll never get 2 turbochargers operating or performing in exactly the same way either. So we'll go into the programming, we'll go into the actual setup, clocking up of the housing, setting up the tool, creating the datum for those guys that work on CNC machines or are interested in engineering, to the actual machining. It's about a 4.5 minute, 5 minute machining job, to the actual finish you can expect, to the cleaning of the entire turbocharger, reassembly of the components, balancing high-speed VSR balancing of the CHRA, installation back into the end housing, setting up of the orientation, and onto the flow bench, which a lot of people locally also don't have access to. So you'll find that on VNT turbochargers, you need to make sure that you have your midpoint and maximum flow settings correct. Otherwise, the turbocharger is going to be laggy, it's not going to perform properly, you're going to get engine lights, you're going to get limp mode activations and all sorts of things. So we have a flow bench, and we've gone and created our own base maps from the designs of our billet compressors, and obviously the changes they make to the midpoint and max flow settings. So we'll show you that entire process as well. And once we're done, we'll basically get this installed onto a vehicle, get it onto the rollers, and show you guys what sort of horsepower you can expect at what boost pressure reliably. Now, once again, we've been on this singing the same song and extracting the same blood from the same stone for months on end and video after video. Always keep in mind, a hybrid turbocharger is marketed based on the horsepower that it can make at a certain boost level. Now, if somebody purchases a 400 horsepower turbocharger capable and at 1.5 bar gauge pressure does not achieve 400 horsepower, well, what do you think he's going to do? He's going to increase the boost pressure until he sees the 400 advertised horsepower that the turbocharger can make. And that's where a lot of the reliability issues are coming into play with hybrid turbos. So we'll show you the vehicle on the rollers to see exactly what power you can expect at what boost pressure, and we'll go from there. Let's move on down to the workshop now, and let me show you the turbocharger that we're talking about, and we'll start the disassembly process and get into it. If you haven't subscribed, if you haven't liked, like, comment down below, subscribe, click on the bell if you want to be notified of all of the new videos as and when they come out. Hope you guys like this one. This is part 1. It's about a 40. This first one's going to be about a half an hour to a 40-minute video. So be prepared. If you're not interested in sitting down and being bored for 40 minutes, then don't watch the video. But we'll see you in the workshop in a few seconds. Okay, guys, we're back in the workshop. Here is the turbo that was removed off the Land Cruiser. It's a stock standard turbo. It's unmodified. It is used. But it is still in good condition. The vehicle was driving, low kilometers, low mileage, and everything's in operational condition. So what we're going to do is disassemble this turbocharger, lay it out so you guys can see all the internals, and then from there we're going to go and show you what we're going to do in terms of upgrading, repairing, replacing, etc. during the entire process. So let's get going. We need a 8mm and a 10mm spanner, and we're basically going to loosen all of the bolts that hold the compressor housing on, as well as the turbine housing, remove the actuator, take the turbine housing off, and obviously then disassemble the VNT so that we can get to the core assembly, and then from there we'll carry on disassembling from there. Okay. Before we do anything, many of these VNT turbos have got little pin locator pins, so you can only set the orientation in one way, but we always make a mark so that we always know that we've set the housing orientation back exactly the way it came. For that, what we do is we use a center punch, and we will locate the oil feed or one of the ports, either the oil feed or the oil return. In this specific case, I'm going to use one of the water ports, and I'm going to basically just line everything up with a small punch mark on the comp housing, a small punch mark at the back of the back plate, and on the turbine housing as well. Alright, so we've got these little marks. These are locator marks, so we can see exactly where the orientation of the two end housings are in relation to the bearing housing, and we can move on and loosen up all of these bolts.
This is the sound of dry bones rattling. This is the praise, make a dead man walk again. Open the grave, I'm coming out, I'm gonna live again.
Here is the compressor housing. As you can see, there's no previous damage. It's intact. There's nothing wrong with this housing at all. Here is the rotating assembly. Let's have a look briefly at the compressor wheel. Hasn't made any contact. There's no damage to the leading edge of any of these blades. There's not much play in the rotating assembly. It's intact and it's in good condition. Right, let's take the turbine housing. What I've done is I've just loosened the bolts, and what I'm going to do now is just I've removed the actual bolts out of the turbine housing all the way around, except for that guy over there. And what I'm going to do is I'm going to take the actuator off so that I can get to that bolt. And how we do that is loosen these 3 bolts that are holding the actuator on at the moment. So also a 10mm. We don't need to make marks like many of the other guys in terms of where the actuator was installed and at what angle, etc., because we have a flow bench, and we use the flow bench to calibrate the VNT mechanism after we've done whatever modifications and upgrades, or even if it's just a repair that we normally conduct on these turbochargers. So we have all of the settings on the variable nozzle, the midpoint and the maximum flow settings, speeds, KPI pressure ratios, etc., which we obviously set up just before we put the turbocharger into its box after we've done whatever upgrades we do to them. Just okay, so all of the bolts have been removed. It's not as simple as just lifting out the turbine housing. It's going to be a little bit stubborn, so what we do is we use a copper hammer and we lightly coax making sure that you don't touch the sides of the blades on the turbine wheel against the housing, because you obviously bend them. Right, there we have the turbine housing off. Wheels touching up against the heat shield. Let's put this core assembly down like this. Right, there's your VNT. Your guide ring seems to be good. And what I'm going to do is I'm just going to turn the guide ring. That's vanes closed. If you look inside here, you'll see the vanes. Those are vanes open. I turn them to the open position, and then what I do is I inspect each of the vanes on the trailing edge of every vane to make sure there's no impact damage on any of them, which in this specific case they seem to be 100% fine. There's free movement without having to use much pressure at all. And what we're going to now do is disassemble this entire assembly, and it undergoes a cleaning process which will happen in the background. In the meantime, what I'd like to do is I'm going to remove the actuator from the crank. That little arm over there is called the crank. I'm going to remove it from the crank, and we are going to disassemble the rotating assembly so we can see what it looks like inside. So in order to do this, we need to get a small flat screwdriver or a spike and take a little clip off. There's your clip. We're gonna watch how it comes off. We will lift the actuator arm, which is basically that hole which goes onto that crank. We'll lift it off, put it one side, and there we have the rotating assembly. Now, obviously we don't want to lose this, so we're going to put this back onto the crank, or we're going to keep it in a little pile with all the other bits and bobs. What I want to do now is disassemble the rotating assembly and show you how this goes together. Let's have a look at and inspect everything inside here to verify that the turbocharger was in fact running in a good condition and it didn't have any pickup on the bearings, it hasn't abnormally thrusted, and there's no existing problems inside before we do an upgrade. Okay guys, so what I've done is I've used some tools just to loosen the nut. We haven't actually disassembled this yet. I'm going to do that now. What I normally do is I just like to take a cloth, just a rag, and just lay it out so that whatever spillage and if any parts or small components do fall out. They fall out onto the rag and I can actually just see them. So remember, this nut, if you have a look at the compressor wheel, that's the direction of rotation, so it's clockwise looking at it. Turning it clockwise, keeping turning it clockwise. If you look at the turbine, it turns anti-clockwise. Compressor clockwise, and that is the correct direction of rotation. So many people will say, oh yeah, you guys didn't tighten the shaft nut, we want a warranty. Well, let me show you something. Direction of rotation and how you tighten the shaft nut is in the opposite direction of rotation. Okay, so I've loosened the shaft nut there, as you can see. Now, that's direction of rotation. If I hold the compressor wheel, to tighten the nut, you go opposite, anti-clockwise, to tighten it. Not possible for a shaft nut to come off or loosen, unless there are certain circumstances, which will be for another video. Shaft nut. We don't reuse this because it already has a balance cut on it from the VSR balancing process. Okay, this specific one does not. So you'll find that that balance cut was taken on the nose wheel of the compressor. That nut then can now be reused. If there is an existing cut or grind on the shaft nut, cannot be reused. We replace it with a new one anyways. Compressor wheel comes off the shaft. Sometimes they're stubborn. This one's coming off nicely. A little bit of oil leakage at the back, which could be because of transportation. If you leave a turbocharger lying like this, obviously the oil will seep through the split seal ring. It's designed specifically in that way. Leading edge of the blades are good. No contact between the housing and the side of the blade, the edge of the blades. I'm happy. Right, let's get the shaft out. Shaft's very simple to get out. You just give it a touch. Pops out this way. Note the heat shield, concave. That's not how you put it in, that's how you put it in. You can see the turbocharger is still new because you can still see a very clean, it's not even suited up at the bottom of the heat shield. Okay, right, shaft. Just give it a clean. It is a water-cooled turbocharger, so you'll find that that's your oil out, oil in, and water in and out on one face. So it is a water-cooled turbocharger. However, you have seen a little bit of discoloration. It's not abnormal. If it was abnormal, you would find that it would be associated with quite a lot of bearing wear, which you'll see just now. The ring is still loose in the ring groove. There's no carbon buildup behind or in front of the ring, as well as the air oil separator, which is the second groove there. So I'm happy with the oil sealing system, at least on the turbine side. Right, there's no amount of soot that's coming out of here, so it further verifies what I've just mentioned. You just clean that sealing face up, hold it up to the light. There's no score marks. The recessed stop is still in place. So I'm happy with the bearing housing so far. Next step, I'm going to loosen these Torx bolts and take the back plate off. Okay guys, we've got the tool that we need, which is a T20 Torx. These are normally have got Loctite on them, so they are normally quite tight. You just need to be careful with how you loosen them. You can strip these quite easily. We replace them anyway with new ones, so it's not the end of the world if we do strip them, but we obviously don't want to damage or break off a head in the bearing housing if we can help it. So once you've loosened these Torx, you can then obviously just unscrew them, and you'll see how the back plate now comes off. So very, very simple. There you go, here's your back plate. It's your bearing housing, let's lay it down. See, another reason why I like to have a cloth handy, either that you lie on or a separate one, is once you've removed a component, you can just use the same cloth and clean up the bits and pieces, and then obviously inspect the critical areas. So there are some certain areas on the backplate that need to be inspected. This is your thrust spacer, which basically, that face over there, the outer face, will mate up onto the thrust collar, which houses your split seal ring, and it sits in the middle of your thrust bearing. So I'm going to put that aside. Just want to take a piece of this cloth and just wipe off the thrust faces or the thrust pads on this bearing, which are obviously critical components. I'm going to pop out from this side the thrust collar, which comes out relatively easily, and I just want to give it a clean or a wipe, and I want to inspect the back plate. If you have a look in the sun over here, I'm glad the sun is shining where it is today, the ring has not even discolored. It's still the brown color that it is supplied as. On the actual face, the mating face, which mates up against the thrust pads over there, there are no score marks. There is a slight witness mark, so you can see it has run, but nothing to be worried about. I'll inspect this back plate quickly, just give it a clean so I can see the inside of the... I'll hold this up to the light. I'm more than happy with the back plate. Back plate land. This can be reused. Right, let's take the thrust bearing out. Just turn it around. It does come out very easily. You just got to break the oil film. Right, let's clean this thrust bearing, and we inspect the pads. Now, the orientation of the thrust bearing is like so. Now, remember, this side here is the compressor side, which the direction of rotation is clockwise. This side of the bearing faces the turbine side. The direction of rotation is anti-clockwise. Now, the pads, these pads over here, are not flat. They are angled to swipe the oil between the thrust collar, the mating steel collar, and the bearing itself. So if you hold this up to the light, where you see wear on a thrust pad will, in a clockwise direction, will be on the leading edge. So those sides of the pads over there are essentially your high spots, and that's where you would normally see wear. This bearing has not worn, and obviously on the opposite side you would see it on the reverse side of the pads, the trailing edge. So this bearing can be reused, but we will not reuse it. So it's just a rule of thumb. We do not reuse any bearing component, even if the turbocharger is brand new. We need to make sure we know what's going on inside that turbocharger before we can put our name to it. So that'll basically go there. Next step is just wipe this inside. Here's your mating thrust washer. There you can see a witness mark. I don't know if you can see that shiny face, that shiny area, shiny outer circumference. That is where the face mated up against those pads over there. Right, this is a semi-floating bearing system, which means that the shaft rotates inside of the bearing. That's the bearing there, and that is a locking pin which prevents the bearing from turning inside of the bearing housing. So less coefficient drag, only the shaft rotates with drag between the bearing inside diameter and the shaft outer diameter. Whereas a full floating bearing, the bearing turns inside of the bearing housing and the shaft turns inside of the bearing itself. Very easy to get out. Just got to be a little bit slightly aggressive. There is your locking pin. Here is your journal bearing. Right, there's your scallop, the little cutout on the journal bearing, which obviously orientates itself there, and this little locking pin over there will basically slot in there, preventing the bearing from turning. So I'm happy with the fact that this bearing housing is still intact,
And another telltale sign if a turbocharger has overworked or if it's seen a thermal overload is this O-ring would be melted and would have started migrating. That's the metallurgical term. It would have started to develop a rough face, a rough surface, which in this specific case it has not. Obviously this gets replaced anyway, but that tells me that the turbocharger did not run at very high temperature. I'm going to get back to this journal bearing now. And the general appearance of the bearing housing is acceptable as well in terms of the thermal discoloration. So I'm happy with that. Let's get something through this journal bearing so we can just get it cleaned. And then I just hold it up to the light and just have a look and see if there are any telltale signs of any wear, any abnormal behavior that's been going on between the shaft and the bearing, which might be due to a lubrication related issue or not, or otherwise not. So let's hold this up to the light. I don't see anything that we need to worry about. If you put the bearing in the correct orientation like that, back onto the shaft, there isn't much play. There's a really rudimentary way of checking the play. We're obviously going to put this into between centers and run a dial gauge on this to be able to check and verify the actual play on the rotating assembly. But just to give you an idea, locate the bearing on the shaft more or less in the running face, hold the bearing and just move the shaft up and down slightly, just to give you an indication. This is not an accurate way, this is not a rule of thumb, this is not how you do it. Don't go and do this as a common practice to tell a person whether or not there's enough play or too much play or too little play. This is just to give yourself an idea of, is there excessive play? No, there isn't. Great. To measure this, you need a dial gauge. You need to put this between centers. That's why there's a hole there, and that's why there's a hole over there. Once it's between centers, you can put the dial gauge onto the bearing, and you can move the shaft, move the bearing on with the dial gauge on the one side, move the shaft, and you'll actually see an accurate value on the dial gauge as to what the clearance is, and you can verify the specifications. Right, so I'm happy with the rotating assembly. We are going to be reusing the shaft. We do not clean the shaft surface, because when you do that using an abrasive, if you zoom in with a microscope, you actually start to create what we call initiation marks, where you'd actually find a shaft fracture if it had to go into a cyclic fatigue or a life cycle. After a long while, you'd actually find that the shaft will break. You do not do any of that. You do not use 1200 grit sandpaper to try and get the thermal discoloration off at all. There's no damage on the shaft, there's no scoring on the shaft, you can reuse it. Obviously what we do is we just tape this up, blast the ring groove, make sure everything is clean with a non-abrasive blast media, and then obviously with the new repair kit, we will replace the split seal ring, the thrust collar, the split seal ring. These are all the components that will be replaced, as well as all of the mounting bolts, etc. So I'm going to leave those out for now. Shaft does not get replaced. O-ring, which seals on the back plate onto the bearing housing, thrust bearing, thrust washer, thrust spacer with its split seal ring, journal bearing, the 4 bolts that hold down the back plate onto the bearing housing, the spacer which sits inside of the middle of the thrust bearing over there, the locking ring, and the nut. This is what we replace, and obviously our billet compressor together with the shaft. And then we will do the CNC profiling, which we're going to move on to next. Okay guys, so we're at the CNC machine now. What I've gone and done is I have loaded the housing onto the machine, and we have clocked it up. So as you'll see now, we've got about a run out of about 0.05, which is more than acceptable. It's inside of tolerances, and everything obviously starts off as a drawing, and then obviously it goes and gets converted to X and Y coordinates. So we're just going to go into program quickly. Going to go to local. Let's open this program up, and that's pretty much what the program looks like. That's the entire program over there. And what we're basically going to do now is we're going to just get this machine zeroed. I'm just going to go back to home. We're going to remove our clock gauge, and what we're going to do now is install our tool, and then you will see pretty much what we're going to do. So there's two different, or not two, there's quite a few different tools or inserts that you can use for engineering. This is a general purpose type insert, which you can basically see over there. Let's get the focus on this guy. And you can cut pretty much anything, aluminium, steel, whatever the case might be. This is what the insert looks like when it is out. And when you're cutting aluminium, or when we're cutting aluminium, we use a very special insert which has got a very high chip break angle, and it's designed specifically for aluminium to give you that finish even without using lubrication, which in this specific instance we're not going to use. Obviously you're not going to get a decent video on how this works. So let's get this tool in. This is tool 4. Let me just tighten this guy down. And what I'm going to do next is I'm going to just write a little program to get this guy running. And okay, G97, that's just a speed of 550 in an anti-clockwise direction. There you can see the guy will move. And what I'm going to do now is I'm just going to set the coords. I'm going to set the datum for those guys that do engineering. I'm going to basically just tell the machine where the Z0 is and where X is in relation to the exact size of what X is. So that is Z, that is X. So I'm going to basically just get this guy come up to and just touch the surface that you're here now. Just make some space so Mike can get his camera over here. Climb up here, Mike, and just get the camera on here. Try and zoom in or get the camera as close as you can to that. I'm just going to move it until we hear contact. Then we know that the tool is touching the face. There we go. And I'm going to now enter that into the program. So you can get a picture of the screen if you want. Go down there, measure Z0. That's Z0, okay? 0. Right. Now we're going to basically do the same with X. So I'm going to move Z away from the face, and I'm going to move into and take a small cut with X in the X axis. And once I've taken the cut, I'm going to do a measurement, and I'm going to program that into the machine so that the machine is basically it knows exactly where it's standing. So excuse my head. Right. It's just started to touch, as you can hear. And I'm going to just take a cut manually. There's no lubrication here at all. Go back in again and just go all the way through the other side. And then I'm going to take a measurement. Right, we'll leave X in that position. I'll stop the spindle, put an inside caliper. And we're just going to take measurement. This is our vernier. We're sitting on 45.3 millimeters. So I'm going to program that in. You say measure X is 45.3. Watch that value change over there on the X axis as I press OK. Now the machine knows exactly where X is in terms of a 45.3 millimeter diameter. Right, now the next step is pretty much a simple one. Go to program, local, load this program, and I am at the very first line over there. I'm going to go to position so I can see the remaining movement that is programmed, the relative, the machine's address, and the absolute. So these are all engineering terms. I'm not going to go into that right now. I'm going to zero the machine. and we are going to press auto. Now if I press start, the machine will run and do the entire job, and it will basically take about 4.5-5 minutes, more or less, plus minus, to do the actual job. It'll finish it off and everything will be ready for installation. What I'm going to do is I'm going to press single block, and I'm going to just press go after every step, so you guys can see step for step what is actually happening here. Before I press start, I'm going to just ask Mike to go to the other side so you can actually get a better view of what's happening. Okay guys, so what I'm going to do now is I'm going to press start, and it selects the tool. It's programmed the RPM. It's going to it's going to start the spindle, and it's going to move the cutter 50 mils in front of the job, and it's going to take the cutting face to 45 millimeters. Okay, now this is going to be running a G96 cycle, which is a constant surface speed. Now that basically determines or ensures that the surface of the material or job to the cutting face remains the same no matter where you are in the diameter. So the closer you get, the faster the machine will start turning. The further away you get from the center, the slower the machine will start turning. Obviously to maintain the same constant surface speed between job and cutting face. Right, so we're going to basically move to 50 in front and 45 millimeters. That's 50 mils in front of the job. That's exactly 45 millimeters, and we're going to take the first cut. It's going to switch the coolant on. So as I press for the next step, I remember I'm doing this single block. As soon as that happens, the water will switch on. I'll switch it off immediately. It comes to 1 mil in front of the job, and switched the water on. I just I caught it and switched it off, and there goes the first cut. Right here. So it's going to take the first cut. It's going to open the hole up to the inducer size of the compressor, and then it's going to come back and start cutting the radius. Do a swipe, a finishing cut, and then I'm going to leave 0.2 millimeters of material behind so that we can do that at a higher speed and get us a nice finish. That's 48.8 millimeters. Comes back out, and then you just blow some of that away. I'm going to use a little bit of Q20 to lubricate the tip. Only a little bit, just on the actual cutter itself. Right, now we're moving to 50.8 millimeters. That's going to be the inducer size. Which should be the last cut that it's going to take before it starts the radius profile. Right, radius profile. Next radius profile. Next radius profile. So what it's doing is it's taking cuts coming out, and it's eventually going to come back in and do one foul swoop. I like single block because you can see exactly what it does step for step. A little bit more lube. And next step. Next step. Next step. And we'll do that all the way to the edge of the back plate, which is 105 millimeters diameter. And then from there, you'll notice that it's not making contact on the back plate at the moment because I've left a 0.2 millimeter finishing cut. So the last cut will take 0.2 mils. It'll just lick the surface and then do the final high speed pass to give us a nice finish. So you'll see it actually stops. I press the button each time. When we take single block off, obviously this is just one fluid motion. This obviously takes a little bit longer this way, but I'm doing it just so I can show you guys. Right, so this is the next procedure. It's going to come forward, cut away all of those ridges. Watch the job start speeding up the closer it gets to the center. Constant surface speed. And it'll come back out again once it's finished. Notice the finish, guys. It's an absolute mirror finish. It's exactly the same as an OEM turbocharger would look. That smoke you're seeing is obviously the Q20. Getting hot between the cutting face of the job and the insert. Alright, the next step will basically come out. Start speeding up because it went closer to the center. I'm going to come back out to 50 in front of the job at a higher speed. You see the water, I switched it up there. Right, coolant off. And watch this next step. Here comes the final cut, guys. 0.2 mil. Oh, here we go. Keep your eye on that area of the back plate over there, or should I say the diffuser area. You'll obviously see where that's the progress of where the cutter is at the moment. Alright, now it's going to do the radius profile. I've taken single block off. Sorry guys, let me just, don't do this. It's reckless, it's dangerous, don't do what I do. For those guys that are going to be anal about safety and how can you put your hand in a moving machine, and yes, I know that. It's wrong of me, I apologize. Slap me on the wrist. Okay, and I'm going to blow this out. That, my friends, is how we machine a compressor housing. This is a mirror glass finish. We didn't even use lubrication. It is a 100% identical radius profile to that of the matching compressor. How? Because we design and manufacture the compressors ourselves, and the same drawing that we use for the compressor wheel gets used on our radius in the housing. Next, what I'm going to do is I'm going to hold this up to the light once I remove the housing from the chuck, and I'm going to show you that there's absolutely no light that will shine between the blade profile and the profile of the housing.